So we're running a little late on time, so I'll try to move through this a little quickly. I'm going to present 2 talks on behalf of my students who would have been here, except they're down presenting some of this material to Google. It looks like some of this technology may well be deployed throughout that campus, and others. We'll keep you posted on that. So let me first touch briefly on SMAP, Simple Measurement Actuation Profile. This is part of the technology developed through a variety of programs, 2 in particular funded through the National Science Foundation that were adapted and extended for use in this project. At some level, SMAP seeks to do for physical information what XML did for documents. And that means create that narrow waist so that you can bring together a wide variety of physical information for a very broad set of uses. And at some sense, that's about homogenizing. It's partly that it's layered, but what's really critical is that almost anything can be used in any way. Of course, it's built up on a classic web services stack with JSON at the top as a machine-readable object document. So the thrust here is the thing about physical information is it's so incredibly diverse. And that means managing that heterogeneous capability and bringing it together into a common framework. Not just for monitoring, but for actuation was considerably harder. And in particular, in the course of this project, it really caused us to focus. In addition, of course, you bring all of those modern wireless sensors and whatnot to pay a great deal of attention to existing repositories, as well as existing systems. What we found, I'll touch on a bit of this, is the second question out of how do we get my system working is now how do you incorporate the data I've collected over the last N years into that as well. It was about scalability, both outwards in terms of number of points. We have something like 30,000 points. Inward in terms of points in the building, about 6,000 points in this building, and across different domains, different kinds of information. In particular, that pushed issues of intermittent connectivity. Even if it's IPv6 everywhere, the IP service to your home, for example, Mary Ann's home, is quite intermittent. You don't have to be mobile to do that. Also, it's about harvesting all of the metadata that's gone into those systems as facilities were put together. Part of it is about being able to do control on top of this, and that means very quick, what's classically called remote procedure calls, and as well to be able to work either with high-frequency data at a great deal of detail over years and years, and be able to scale the time frame of the demand and of the queries essentially with constant response time, and as I mentioned, a wide diversity of applications. So the structure of SMAP, it's partly a representation, and it really is partly a software architecture. So what this picture tries to convey is, in addition to kind of the classic computer notion of client on your right-hand side and back-end servers, you then have additionally the connection to the physical world on the left. So all 4 of those interfaces turn out to be critical. The physical world to the archival back-end, the physical world to the interactive uses directly for various visualization or control, and as well the connections between those front ends and the back end. And I've touched here on some of the main issues that drove the design of those different aspects. Representing and transmitting not just the data, but the metadata, abstracting the underlying heterogeneity of all of that physical information into a common model. Within the classical back end, it's about access to archive data. It's about managing the very different views of physical information. Whereas in the right-hand side, part of it is that there is no one stovepipe here, that in general you need to be able to craft the front end in a very application-specific manner, such as what was important in the New York Times building that you saw earlier today. So what is SMAP? It's partly a universal information representation for physical data, self-describing, compact, JSON, transportable, integrating the metadata, and it's also partly a software architecture for doing physical data processing well, and that means both for real-time and archival. A key piece of it is the software engineering so that you write adapters once. There's all kinds of different stuff out there. You really want to reuse that effort so that if anybody has adapted something, you can pick it up. And then beyond it is essentially extending the kind of idioms and techniques that have created the database world to extend that into physical databases. And doing that within a resource-oriented framework. So part of that is, at the lowest level, is meeting your data acquisition needs. And you've seen throughout the day some of the work in integrating various BMS systems, various databases, various wireless devices, and so forth. This just gives you a sense of that. Currently, about 15,000 different kinds of things that are swept up into the SMAP repository. And if you will, the most important infrastructures become valuable when they become uninteresting. So that's really the goal here, is to make physical information and working with it as uninteresting as possible. Really, this is the second or third round on this. There's many things like it out there in the world, Smart Energy Profile, various things in this catalog. The key here, I think, in Berkeley is really a matter of eating your own dog food, really building things and then using them and learning from those. And just to touch on some of the key pieces there, it's about part of the focus of the SMAP work during the duration of this project was really, if a new kind of information needs to be brought into that ecosystem, let's do that as easily as possible and harvest as much of the fruits of previous efforts to bring information in. It was about dealing with the various ways that it happens, because it does. In all facilities, you have various kinds of outages that you need to coast through. It was about really harvesting as much information as possible that has been built into these complicated physical systems, such as your BMS, anything that the facilities might have brought in, as well as moving towards the path of really generating these drivers automatically and a growing driver license. So this stuff is all out there under Google Codebase. It's now being picked up in quite a number of places around the world in various companies and facilities. So it has significant legs. It's not the kind of open source project that has 1 million developers. Primarily, it has 2. Which is to say, like all good pieces of code, it's the size of a jazz band, or maybe smaller. But the key is really its ability to move forward. And that's minimizing a source. So this gives you kind of a picture of the SMAP ecosystem. You've seen some of the Acme devices we developed. At Building 90 for a while, we had 800 of those, monitoring roughly half of those. We've built a few tens of thousands of those. Modbuses, RSA, BMSs, weather, the ISOs, all of that kind of information you need to bring together if you're going to do the deep analytics. And you've got some of the sense of the now innovative ecosystem on the application side. Of course, everything you can imagine. If you can say there's an app for it, there probably should be. And I'll touch on a few of those. And yes, there's things that are like Facebook and Placebook, and the kind of innovation that we expected once it was not a fundamental hassle to write code means that you can write code that's innovative. This just gives you a little bit of a sense of that. A couple of undergrads put together campus-wide portals in a matter of a couple of weeks. Stock browsers, because there's always, you got to look at the information before you know what to do with it. A sense of some of the portals for things like this building, which are integrated with various occupant feedback. I'll say a little bit more, just to kind of give you a sense of, yes, it's beginning to make a difference where we have innovative software. So that's SMAP in a nutshell. If there are questions, I'd be happy to take them. Otherwise, I'll go impersonate Andrew Kyorkov. Sure. So device discovery is one little piece. It provides a facility for doing that. The actual means of discovery depends a great deal on the kind of devices that we're talking about. So we certainly harvest the backnet discovery. That only touches the infrastructure. There's a variety of techniques when you're thinking about classical information devices, printers and fax machines and all the rest of that. That's swept up typically through autoconfig is the IETF protocols, or MDNS if you've looked at some of that. So those are some of the different ways of doing discovery. We built adapters for those into SMAP, but more importantly, it then provides the infrastructure for capturing that metadata. So a bit of a yes and no. If you haven't but followed the autoconfig work, it's an important one to look at. It's kind of providing the baseline, the follow-on to universal plug-and-play. Okay, so let me now impersonate Andrew for a minute while he drives back from the South Bay. So you've had a sense of this building. Much of the technology was developed in relation to even more ambitious views of, if you will, continuous demand response, or even creating an information plane for the grid. This is not a trivial challenge, however, to talk about even something as simple as shedding 30%. Part of the challenge was it was 30% of a well-defined piece of the load. You've already seen that the infrastructure consists of two proprietary networks. This is two of the proprietary networks, as of course there's always many such things. It happens in this building that there's one proprietary system that squeaks a little bit of BACnet out the top for lighting, and another that squeaks it out of the top for HVAC. And of course, BACnet is a standardized protocol. What's standardized really is the representation of things that look like integers and numbers and identifiers. What it doesn't begin to speak to is really what's the semantics, what's the relationship, or what's the programming model. So part of what you've seen now is sweeping these and many other things up into web services architecture so that we can talk about programming. But of course, what's really important inside of buildings is the very complex dynamics, which Steve Selkovich touched on this morning. This is just to give you a sense of it in this building, which is typical of many. If you just think about what are the family of interacting control loops that, of course, interact not through an information exchange, but through the exchange of various media, whether that's water or air at various temperatures and pressures. So think about the cooling tower loop talking to the chiller loop through the water that got chilled, as well as the hot water loop, the economizer, which is a different kind of loop, mixing fresh air with conditioned air, the various air handler loops maintaining the effort in the supply and return fans. Each and every one of the 140 VAVs is its own control loop. All of these busy doing their thing relative typically to a small family of set points. Okay? And you've seen a taste of some of the behavior. It is a marvelous thing that these things work at all. It's not surprising that they work incredibly inefficiently, and in particular, that they really don't scale well to variations in demand, and hence are not very responsive when it's time, for example, to shed load significantly. So part of what we were focused on here, using that infrastructure, how do we go tackle the problem of collections of oblivious control loops? And for example, if it seems that demand response, that ought to be easy, let's just raise the temperature on the thermostats. Well, in this building, we take reasonably comfortable air, cool it down to an incredibly cold temperature, push it real hard throughout the building and reheat it. So raising the temperature only means that we'll reheat it a little bit more. So many things are not at all obvious. And in fact, in many cases, those control loops may be fighting with one another. And yes, indeed, it can be hard to modulate it well because the infrastructure itself is oversized. So part of what we assembled, part of what you've seen, is really now to extend that web services to a kind of higher level control. The kind that allows you to build models so that you could start to use modern model predictive control strategies, which is the heart of the Action Webs project here at Berkeley. So just to give you one simple example of that. In fact, campus has this theme of really treating its facilities as a kind of living laboratory, this has become one. In particular, this entire building is programmable. Various efforts, you heard from Ranjan earlier, work with Francesco Borriello's students, needed essentially to conduct experiments upon this building at various times. So what you see here is the equivalent of the batch job entry that was typical of computers in the 60s, but for a building, where various folks in various fields, control, in mechanical engineering, essentially could submit scripts or various experimental plans, pass them through an approval stage, which consists of Domenico in the back of the room, and then have them submitted and run according to a schedule, perhaps underneath a sandbox, so that if those efforts went outside of certain safety bounds, they would be aborted and the building brought back into appropriate, as well as now incorporating that into a data collection infrastructure. In fact, this technique went much further. In many cases, it's not just a matter of characterizing the step response of the building, but integrating that with control algorithms or with various kinds of real-time diagnostics. So the experimenter over there in Echeverry could have their MATLAB system running, implementing the other half of the controller, and at the point in time where their experiment runs, then the building would be engaged with their higher level control loop. So in some sense, we built the predecessor, the prototype of what now is becoming a much larger project in software-defined buildings. How do we begin to make buildings do beyond what was their original design intent? This just gives you a sense of that. You can see a variety of different researchers throughout the institution submitting various jobs, if you will, that are literally actions to be performed over time on the building to be able to develop some of these demand response and continuous demand response or model-driven predictive control strategy. That was just a taste of many such applications. Some of you got a sense, many of the folks in this building now have direct personalized control. There's special portals for the building, extensions of the building portal that Domenico sees that feeds that information back. As we've done things like do static pressure resets and whatnot, we've actually been able to observe how people perceive that by where did they insert the overrides and so forth. Let me just finish on just a couple of quick examples if you think buildings are simple things, closing at where Stephen. This is a picture of what the building looks like to the 140 or 4 VAVs throughout the building. The black is the average, and you can see that on average, we heat it up at night and we cool it down in the day. Cool is towards the top. But if you look at that individual community, they're all over the place. And in fact, if you dig deeper, you'll find there's all sorts of places where you can identify the simultaneous heating and cooling that you need to go in and undo. For example, yes, we'll never cool the boil room, but you'll notice, for example, there on the 4th floor, places where essentially adjacent thermostats, one is maximum heating and the other one is maximum cooling. And of course, there must be an air exchange between. So using this kind of ability to really see what's going inside, we've been able to look at how do we get to where we pay attention to the actual occupancy when we're determining the amount of fresh air that we're driving, and how do we move things back towards a kind of minimum level of delivery for that. And this just gives you a little sample of things that you couldn't necessarily do with the infrastructure built into the building. This is saying, let's let the variable air volume, whose job it is to deliver a certain amount of fresh air to the occupants, know how much fresh air is coming in through the economizer. And there you can see in the blue the kind of mix. So this is an example of a kind of whole building control that in the future will be typical and today is rather difficult unless it was wired for that particular substrate. A different one was we were supposed to shed 30% of the office load. It turns out of the 900 kilowatts, first you break that down into several hundred point meters, and then you have to build it back up to figure out where that went. To get to a picture as simple as this, where you can say out of that, there are 135 on average kilowatts going to the office. riding on top of 600 kilowatts in the fab that we're not supposed to touch, and another 70 or so in the IT infrastructure that we're also not supposed to touch, so that we could then take that and break it down to see how much we could go after in each of the elements associated with the dry loops, and then you go after actually doing it. So that notion of disaggregation and reaggregation also has to become an absolutely natural part of this, which is why you need a more substantial information infrastructure. So that was just a taste of some of the kinds of applications then built on top of that infrastructure.
Thank you
Thanks.
very much, Steve.